Hello everybody and welcome back to the continuation of our lecture series on frame listeners and input-output interactions with our Ogre applications. In the previous video, what we did is we established a Ogre application, placed a Sinbad node on the scene, and then we utilized what we call the frame-based movement implemented through our frame listener mechanism. So frame listeners are effectively, as we talked about it in the last video, they are observers. So effectively, they are a class interface that are tied to the core operations of our subject class. And then when certain events happen, then these observers will basically get updated. In the case of frame listeners, they are exactly what they say. They listen to frames. So they are going to be updated when certain activities, certain things, certain events happen to our frame renderer. Which basically, the simplest way of looking at them is that when a frame renderer, when a frame buffer is being rendered, two certain events are of importance. One is when the frame is being started to be rendered on the scene. So as soon as a drawing occurred on your monitor, basically, and then one when the rendering ended, so when the drawing is concluded. So these two functions in our application, in our frame listener, are the frame started and the frame ended functions. And both of these functions work on a per frame basis. What that means is that when the frame started starts whenever your rendering mechanism will start rendering the frame. And then frame ended basically happens at the end, at the conclusion of when the rendering occurs. And as a result of this, these functions depend on the frame per second speed of your computer. So if you're using a computer that is fast, then in a second, let's say 120 frames are being rendered. That means that this frame started and frame ended effectively happen 120 times. If you're running on a computer, on a slower computer, then in a given second, it might run 30 frames per second. That means that over a span of 1 second, you would have 30 of these frames operate. So for example, what the problem with this is, since it would be dependent on the speed of your computer, so if you have a same amount of time, for example, a span of 1 second, in a faster computer, these things would fire many more times than they do on a smaller machine. So a faster computer, they may fire many more times, whereas on a smaller machine, they may fire, or a slower machine, they may fire with less frequency. So tying into actually a frame-based movement or a frame-based mechanism, the translation or the movement of your objects or any kind of animation with your object would change the speed of your animation, would change the speed at which your objects would move about in the scene, because depending on the speed of your computer, which is not really a good idea to do. Also, on top of that, in order to get accurate representation and accurate simulation, there may be even another problem that may not depend on the differences between two computers, but rather also may occur on a single computer, on the same computer also. And that's what I'm showing here at the bottom. We may have a situation in which frames, when they are being rendered, they may actually render not at regular intervals. So what happens, for example, is that the first two frames just happen to run at a shorter time span, because the computer at that point may not have got too busy, whereas the next two frames had a little more irregularity in terms of the time difference between them. And so if you wanted to represent a very accurate simulation, physical simulation, you wouldn't really want to use per frame or rather frame-based movement. And it would be really useful for us to be able to also include and incorporate the time difference between when two consecutive frames occurred or rather fired. So the solution to this problem is actually to use the frame event. A frame event is basically a variable that the frame started and frame ended functions will get as input, and so this will evaluate the elapsed time between two consecutive frames, and it gives us, for example, access to time since last frame value that then we can use. So here's an example of it. So let's say that we have a frame-based movement, and let's say that we want to move our car 10 units, kind of like thinking of these 10 units as a measure of its velocity, how fast we want the car to move. And so let's hypothetically say that our frame number 1 rendered at time 0, then frame number 2 rendered at time 100 millisecond, then frame number 3 took 300 milliseconds to run, so at time t 400 milliseconds, frame 3 updated, and then frame 4 updated at 550 milliseconds. Now, we have 4 frames over a span of 500 milliseconds. If we use the frame-based movement that we just did in the previous video, we basically took the object, in our case the ogre, and we moved it, let's say that 10 units. So we translated the object 10 units to the right. If we use frame-based movement, our car basically starts from location 0, goes 10 units in the next frame, goes 10 units in another frame, goes 10 units in another frame. So in total, the car moves from location 0 to location 30, which basically, visually, you would see that it's moving very, very slow. Also, it's not accurate because the time that it took between different movements effectively were not equally spaced. So although the car moved at equal spaces, it actually would show that it's slowed down and then sped up and then slowed down and so forth. So so frame-based movement in this case is not going to be accurate realistically and physically for us. In the time-based movement, what we're going to do is we're going to use, for example, this 10 units of movement as a measure of our velocity, v. And then we can use the frame event and take the time since last frame as a delta t, which would be the time that it took between the 2 frames to elapse. And then use that value and multiply it by the speed as the actual displacement measure for our object. So between frame number 1 and frame number 2, it took 100 milliseconds, and therefore the car moved 10 units. Then between frame number 2 and frame number 3, the time difference was 300 milliseconds. If we use that 300 milliseconds here, then you would see that this value would amount to 30, which then adding 10 from the previous value to it, then you would actually go and get placed at location 40, and doing the same thing, taking the displacement, multiplying by velocity, then the actual displacement for you will be 15 units. From the 40 units, you would go to the actual 55 units as the actual location of the car. So using time-based movement would solve the problem of inaccuracies in our simulation, and also makes our application, especially when we're translating, rotating, or moving objects, if we have dynamic animation, dynamic simulations, the time-based movement will create much, much more accurate representations of whatever we are intending to do, and make it more platform independent or machine independent. So if we have a fast machine that renders many frames in a given time, the time between these frames would be smaller. Therefore, the two cancel each other out, and the movement of your object would be the same as if you had a smaller machine, which renders fewer frames in a given time frame, but the time difference between those fewer frames are going to be higher. So, so this time-based movement cancels out the speed of your machine and also the irregularities that may happen even within the same machine running multiple frames and rendering your frames. That being said, in many situations, we might be able to just get by frame-based movement when we are not really too interested in accuracy, whereas efficiency in terms of how fast our application runs. So we don't want to actually do these complicated computations of multiplying values by each other and doing these kinds of things. And also, in certain cases, for example, when we're reading movements from, for example, key press patterns from a keyboard, or mouse patterns from a mouse, the differences between these um, rather irregularities in time may not be too important for us. And in those cases, we can actually go about and implement our system with frame-based and not even account the time that it took between multiple frames. So the two applications, the two patterns here, time-based or frame-based, have certain benefits in certain applications. And so it is very important for us to know the difference between the two and when and how to use these patterns. So this being said, next we are going to go and implement in our code the time-based movements. So we're going to create a speed measure, a velocity measure for our object, and then we use the time since last frame to be able to calculate an accurate location for our object and then move the object about. Okay, so here we are in our code now, and I want to just go ahead and implement the time-based movements that we have here. So what I'm going to do then, let's go ahead. So let's create a vector 3, and let's call it speed. And we will make it to be 10 units on x and y and z. And this may be actually small for us, but we'll see how it works. And now we want to translate our object by this speed. So in order to perform this translation, we will take our speed and then we multiply it by the time since last frame. And if you use the EVT function, then you will notice that the EVT value will give you a time since last frame. It also gives you a time since last event. The difference between the two is that the time since last event gives you the time in second that occurred between two events that may have happened. And so it gives you the time between when the frame started and then when the frame ended. Or rather, when the time of when the frame ended to the next time that the next frame started. So we want the time since last frame. It basically gives you how much times did it take your machine between the last time that the frame rendered and this time that now the frame is being rendered. So we're going to use this time since last frame as the measure of our delta t, which is time difference, and multiply that by the speed. Now let's run this and see what happens. All right, now you see that the Ogre, or rather the Sinbad node, is being translated to the left, or rather to the right, at a certain speed. And this speed is relatively uniform and pretty nice. So we can actually go ahead and change this. So if I wanted this to go 5 times faster, I'll just change my speed to vector 350. And now let's run this application. And so now the Ogre runs much faster out of the screen. And if you wanted it to go really slow, with the speed of 5, all we need to do is just to change our speed factor. Okay. So this is the difference between time-based movement and frame-based movement. And next, we are going to go ahead and start implementing our input-output system into our application. So the first thing that we will do next is to start our input system, by which we will be able to actually get the window handler from the operating system, use the window handler to register a parameter list to our window and an input stream that our operating system will create as a part of this, and then create an input manager system. And then use our input manager system to read events from the keyboard. And then we use the keyboard events to look for certain keys. And the first one that we will look for is going to be the escape key that would close our application. And then we're going to go ahead and start reading for W, A, S, and D keys to be able to move the ogre up, down, left, and right according to the keys that are pressed. And then also utilize the mouse events to be able to move our object, rather our camera, to move it around and move its view in our system. Okay, so let's see how we can go ahead and implement our input system. So in Ogre, the input system is utilizing a object-oriented input system, or the so-called OIS, which is a very nice and wonderful object-oriented input library, and it supports many different kinds of devices, including your keyboards, your mice, your joysticks, and so forth. So the idea behind this library is that what we will do is we will utilize our operating system and establish an input system based off of what the operating system will effectively understand as the user's interaction through the input devices with the window of the application that the Windows had started. So there are several steps that we will have to take, and I'll show you in code how this will be implemented. So the first thing is we will create a so-called parameter list, or a param list, in the OIS. And it's basically a type def that takes in a map, and it's used to create a parameter classes for our input system. We will also use a sort of numerical value of the type size underscore t, which is used by our operating system to render, or rather to get the window handler for each window that the operating system renders. What this means is that a window handler, whenever your operating system initiates and creates a new application and creates a new window for that application, it will assign to it a unique window handler, which is a unique number. And so we will use this unique number to associate our parameter list. Since this unique number is an integer, in Ogre we would need it to be a string, rather an O string. It doesn't matter if you use the standard library string or O string. Both of them will represent a string stream, and this will stringify, so to speak, the size t of our window handler. So we create these three variables: a param list, we call it PL, a size t for a window handler, which is a numeric value, and then a string stream for the stringified version of the window handler, which is in the string. Then we will populate the window handler, the numeric window handler that we created. Basically, we will assign the window from our operating system, and then we associate its window value to or attribute to be the numeric size t window handler that we just assigned. Basically, what this m sub win is the pointer to the window that is rendered, and we basically what we'll do is we'll ask our or rather reformat our frame listener's constructor to take the scene node and the window pointer as well, and then we will be able to use the window pointer to populate the window handler. Next, we will take the window handler and stringify that. So we put basically with the stream operators, which is the two less than signs. So we put the window handler and we put its string version into the window handler str, which was the string stream variable we created. Once this is done, we will put the pair of the window handler string and then the window as a parameter list. So we insert the window and its string object as a pair into the parameter list. This parameter list then can be used to create actually your OIS input system manager. So what we will have to do is to create an input manager pointer, and we call it here in this case M input manager. Then we put or rather the create the input system based off of the parameter list that we just associated up here, and we create that as an input manager. So this input manager then at this point on will be effectively looking at the window that is rendered on the screen and reads the input from our OS into the input manager. Once our input manager is established, we create a mouse pointer and a keyboard pointer, and then we'll be able to actually create our input system based off of the mouse or the keyboard. A couple of things that are of note to do is that we will basically do, actually there's a typo, I'm going to change this, so it should say OIS keyboard pointer M keyboard. So a couple of things that are noticed is that these mouse and keyboard are pointers that we create, the M keyboard and M mouse. And then what we'll do is we will, when we look at the input manager and then create the input object for our input system, which then in the parameters that we pass, the first parameter will say whether we want it to be a mouse or a keyboard, then this will effectively return an object, an input object, and we have to static cast it to the type of object we want. So when we say I want an input, create an input object OIS mouse, the result is going to be still an OIS object, and so we will basically cast it into an OIS mouse if we wanted it to be mouse. Same thing if we wanted it to be a keyboard, we will have to cast it out, static cast it rather, to a keyboard. So so the thing that is of notice is that this thing, regardless of what you ask it to create a keyboard or a mouse, it will bring in an OIS object. And so you have to static cast it. Needs to be done to the OIS keyboard or the OIS mouse. The second parameter in the create input object specifies whether or not you want it to be buffered or not. And this will basically create your input objects there. Finally, once our input objects are created, mouse and keyboard, then we can use the M mouse and M keyboard pointers to call the capture function. So we can actually then put the capture function for mouse and the capture function for keyboard in our frame started or frame ended, whichever you want, to basically read what happened at the beginning when the frame was being rendered, or which key was pressed, or what was the status and the state of your mouse. And then we will be able to look into these values to be able to perform our input mechanisms. So now let's go to code and do this and program this input system. So the first thing I will do is we'll establish our input system and create a keyboard object. And once that is done, then we are going to read the keys, or rather capture the keys, and then associate the keys and see whether a key escape was pressed. And if it was, then we return false, basically terminate our render loop. All right, so if you remember, the things that we needed to do is we needed to set up a couple of parameters, and these parameters are effectively a parameter for a parameter list, a parameter for a window handler, the numeric version of it and the string version of it, and then a parameter for our input manager, rather a pointer for our input manager, and a pointer for mouse and a pointer for keyboard. So let's go ahead and establish these parameters. So we would create an OIS param list, and we call this PL. Then we would create a size T parameter, and we call it our window handle. And we would create a string stream, which will represent the window handle in the string format. And let's put 0 in our window handler, basically. So these are the variables that I needed to create. Now I need also to create a variable for my input manager, rather pointers, a pointer for my input manager, a pointer for my mouse, and a pointer for my keyboard objects. So OIS input manager pointer, and let's call it M input manager OIS keyboard pointer, M keyboard, and OIS mouse pointer, and mouse. All right, so these are my my private member variables for the frame listener. And then what we will have to do is we'll have to go and change the constructor of our frame listener to now take all in addition to the node, to take our window handler, which will be of a type render window. So we'll pass a render window pointer, and let's call it M window. Okay, so that's the render window that we create, or rather pass to our object, our frame listener at construction time. So now that we have changed the format of our, or the signature of our frame listener function, we will also have to go ahead and in our create frame listener function from the original application, where it is calling it, we would have to also change that so that it would pass the window, render window, where your Augur application is being rendered. And that render window is actually in a member variable called mwindow. So we'll just basically, at the creation time of our frame listener, when we are newing the pointer to frame listener, my frame listener here, or my listener here, I'm going to pass the Sinbad node and the mwindow from the original application. Now that we have this, these member variables created and our constructor also sort of rewritten, its signature changed so that we have the mwindow, then we are going to use the mwindow object, and then we're going to go ahead and set its custom attributes. So the interesting thing about setting the custom attributes is that mwindow effectively uses the get attribute, and then we pass the reference of our window handler to set the window attributes of, or rather get the window handle and then place it inside of our window handler that we created. So we say get custom attribute window, and here's the reference window handle to set it up. So basically, the window handle that I created up here is a size t variable, and then I pass the reference of window handle into the get custom attribute of the mwindow, and that basically sets the value for me. Now that that has been done, then what I'll need to do is to go ahead and stringify it. So I say window. So I say window handle string, and then outstream, and I call it window handle. It's kind of like a CN CN operation from your OS. Then we're going to create the parameter list. So we will insert in our parameter list make pair, and so the make pair we're going to use is going to be string window and window handle string.str. So what this line of code does is basically it creates a pair with the string window as the first member of that pair, and then the string that is being written into the stringified window version for us in the form of string. So basically, it's like, you know, in your OS, each window has a name called window and then a number associated to it. So we created that kind of same thing here with the parameter list. So now with the parameter list created, we can just go ahead and start our input manager. So we had an input manager that we just created as a member variable, and that will be OIS input manager create input system based on the parameter list. And then we will create m keyboard to be static cast OIS keyboard, actually OIS keyboard pointer, which would be from m input manager create input object and I want it to be an OIS keyboard and the buffering to be false. Then I'm going to go do the same thing for, actually it should be keyboard. And then we're going to go do the same thing with our mouse. So create the m mouse, static cast it to a mouse pointer, and make this object a mouse. This mouse, all these mouses need to be capitalized. Oh, OIS keyboard, and OIS mouse. There you go. Okay, this creates for me my frame listener input system. So again, just going over the frame listener input system, what we're going to have to do is create a parameter list, a window handler in the numeric format, and a stringified version of it as a string stream. And then 3 pointers, one for your input manager, one for your keyboard, one for your mouse. If you wanted to use joystick, then you create also an OIS joystick pointer for your joystick as well. Then in your frame listener, you modify it. First, we create a render in the frame listener signature. We are passing already a pointer to the node. We also create and pass a pointer to the M window, which is a rendered window. And then we are going to have to go in the function call of this frame listener in the create frame listener to modify it to pass the M window. Then after we establish the node, we just read and get the custom attribute of our window handler from the M window, stringify it, and then create a parameter list by calling the pl.insert method, and then create a pair and pass the string window and then the string version of your window handler to it. From the parameter list, then you create a input system for your input manager. And then you create M keyboard and M mouse by calling up the M input managers create input object, one for keyboard, one for mouse. And then you static cast the output of the result to an OIS keyboard or an OIS mouse. And now you have these members created for you. One thing that we'll have to do is, since we created the M input manager, M keyboard, and M mouse in our frame listener as pointers, we will have to make sure that once the frame listener is destroyed, these pointers are going to effectively be deleted. Notice a couple of differences between the scene node pointer and then the M window pointer that we created here. M window pointer that we create here is a local variable, so that's no problem. Scene node that we created up here called _node, we basically are using the node pointer that is being passed to this function. And so we don't have to delete this node. In fact, we should not delete this node pointer. However, in our function, in our frame listener class object that we created, we have 3 pointers that we are manually assigning. So the ones that we're manually assigning are the input manager here, the M keyboard, and then the M mouse. So since we are creating these at the construction of our frame listener, we will have to go and delete them at the destruction of it. So we'll have to create a frame listener, my frame listener destructor, and then go ahead and take care of all the destruction of these objects that we create. So the first thing that we created is the input manager. So since we created it, we'll have to destroy it. So we'll say if M input manager. So if it has been created, then M input manager destroy input object, and then M keyboard, and then M input manager destroy input object, M mouse, and then destroy the input system as well. So OIS input manager destroy your input system, M input manager. All right, so we are now completely set up to be able to perform our input actions. So what I did now in this case is that since in my frame listener constructor, we have manually created our input system based off of the parameter list, and then the keyboard and the mouse pointers based off of the input manager that we created, we will have to go ahead and delete these. And deleting them is fairly straightforward, or rather destroying them is fairly straightforward. You basically see if the input manager has been created. If it has, then destroy its keyboard, destroy its mouse, and then it's kind of like the opposite of create input, create mouse, and then just call up on the destroy input system global method and delete the input manager there. So this is set up, and next we will go ahead and create our test, rather, to read the key value and see if it was escape, and if it was, then to see if it was escape, and if it was, we just return false or rather out of our frame started function. So the test is fairly straightforward. First thing we need to do is to use the call up on the M keyboard capture method. And now that we have the capture method called, every time a frame is being rendered, it captures the state of the keyboard. What happens is that then we can use this state to decide what key was pressed. So we create an if statement that looks at the M keyboard's is key down method, and then the result of this is going to be true or false. So we pass a key that we're looking for, and we want to see if it is down, and so the key is going to be underscore KC escape. So the result is going to be either true or false. If it is true, that means that the key escape is pressed, or the state of the keyboard says the key escape. If it was false, then we basically know that some other key was pressed or no key was pressed at the time of the polling, and then we return false. And remember, returning false out of your frame started will indicate to Ogre that I want to terminate the render loop. All right, so now let's compile and make sure that this input system mechanism was created properly. Okay, my compilation went through, and let's see what happens. So we should still see the Ogre moving to the right, and then this time if we press escape, we should be able to terminate from the scene. So then again, this was a fairly nice input system, nice and easy. We set up here. You press the escape key, and when you press the escape key, your operation terminates. Now, a quick thing that I want to do is also, while we're at it, we're going to also use and check to see if the plus or the minus were pressed. If the plus was pressed, we will double the speed. If the minus was pressed, then we would slow down the speed. So let's go and check to see if keyboard is key down, OIS. Okay, let's do KC add. So if KC was add was plus, then speed times equal 2. And then since I don't want it to go really, really fast, then I'll say if speed greater than 100, then speed equal 100. And then we'll do the same thing, or rather vector 3. Speed dot x, speed dot x. And then we'll do this with the speed dot x. Then let's go ahead and do the same thing for subtract. And then divide it by 2. And then if less than 2, then speed equal 2. So now with the plus and minus sign, we should be able to speed the Ogre up or speed the Ogre down. Okay, so that operation was pretty successful. Actually, let's add 2 to the speed and then subtract 2 from the speed, so that it wouldn't be as quick in terms of its speed transition. Okay, with the plus, you increase it, and then with the minus, you decrease it. And we cap it at 10. Okay, so that was with the speed combination. So let's get rid of those, and now we have our program. So Now that we have this operation, basically, that takes care of our input system and reads the keyboard state, let's go ahead and so I'm going to wrap this video up at this point, and then in the next video we are going to go ahead and start using the WASD keys to move our ogre up, down, left, and right, and then we work with the mouse to be able to get control of the camera back.